So, and you can introduce him, Venus,
Sure.
whenever you're ready.
Absolutely, yeah. Yeah. Hello, everyone. It is my absolute pleasure to introduce Kimmo Tuominen, the speaker today from University of Helsinki. As long as I've known Kimmo, he's been in Helsinki, but yeah, there is obviously before I joined. He finished his PhD in University of Jyväskylä in Finland and did a few postdocs and visiting researcher positions in Odense in Denmark and in Southampton in the UK. And he's been in Helsinki for a very long time. And he is very well known for his teaching qualifications. And having sat through his classes, I know he's an amazing teacher. And today he's going to talk to us about, as you can see, gauge theories and vacuum phases. Please, Kimmo.
Thank you, and thank you very much for the invitation. Very happy to give this talk. And so I'm going to be talking about the vacuum phases of gauge theories, and this is sort of a research program with which I have been involved with for quite some time, and it has different aspects to it. And so I'm going to start with a relatively long introduction and motivation, defining the reasons why we want to look at these things and what they are and how to approach them. And then I'll give a sort of lightning review of some lattice methodology, mostly just underlining some important features which are very different than what we have learned to apply when studying QCD. And then I'll show results from simulations, mostly from simulations which have been done by the Helsinki lattice group. So collaborating with Kari Rummukainen there, and then end with a little summary of what we may have achieved and what remains to be done. All right, so starting from the usual story that the standard model of elementary particle interactions has proven to be very successful model. So all the particles contained in it have been observed. Most recently, the relatively light Higgs boson. And the figures here show the compilation of ATLAS data, but this is similarly supported and completely compatible with also the CMS experiment data. So there is this light boson, which seems to have couplings according to the expectation from the standard model. So the right plot shows the couplings of the Higgs to various other particles scaled with the standard model expectation. So the value 1 corresponds to standard model. Everything seems to be compatible with that, leaving very little room for apparent beyond standard model physics. But nevertheless, equally well, we know that standard model is incomplete. And the usual list of things, so starting with the explanation for the origin of the electroweak scale, which, I mean, this used to be the very big driver of the beyond standard model research, because it was the paradigm was to explain the hierarchy or the naturality issues. And of course, it still is a question that whether there is a dynamical origin for the electroweak scale or not, or whether it's just something that we need to approve as a parameter of the theory. And then this is very much connected with the various other issues, like the question about dark matter, the question about particle dark matter. So in the standard model, there's no particle which could stand in for the observed dark matter abundance. We don't know if it is a particle that we are looking for, or whether it would require rather modification of gravity or some extension of gravity. But the particle dark matter is a sort of relevant and well motivated paradigm based on how we understand the structure of ordinary matter. And then the question about the strong CP violation, perhaps connected with dark matter or not, and the question about baryogenesis, how was the asymmetry between matter and antimatter created, assuming that as an initial condition is not appealing, but one would like to have, again, a dynamical mechanism to generate that. And various possibilities exist on the market, and they all imply the need for physics beyond the standard model.
Can you ask a question?
Oh, absolutely.
What evidence is there that dark matter is composed of elementary particles? I know of none.
Yeah, that's what I was sort of, yeah, I totally agree. And that was what I was sort of trying to say, that that we don't know that it should be a particle. It could well be a modified gravity, or
there are other possibilities in the quantum
or a let's say originating from the inhomogeneities or
the quantum field theory phenomenon. There are many other phenomena in quantum field theory. For example, there are these continuous spin particles of Wigner of mass zero,
yeah,
which have no which cannot be interpreted which cannot be readily interpreted as a particle.
Yeah.
For example, okay?
Yes.
You don't know that it cannot exist.
Yeah, I agree. So and then going down the list, there's the question about flavor, which certainly is should be very relevant. So what's behind the patterns of the fermion masses, which just appear as the Yukawa couplings in the standard model? Why are there 3 generations and only 1 Higgs doublet? All kinds of questions which imply the plausibility of beyond standard model physics. And then the question which I would like to now refine into or focus more is that, so given the standard model, it features the gauge theory paradigm in a very central position. And then if we extend, it's likely that we would need further gauge symmetries or anyways a need to understand well the gauge theory dynamics. So the question that I would like to focus on is that, given a theory, how does it look like at large length scales? So what is the vacuum phase of the theory? And that's what we will be discussing or focusing on today. And so before moving too far, let's just set the stage by looking at something that we think we know rather well, the vacuum of QCD. So taking as an example the QCD Light, so SU3 gauge theory with 3 massless fermions. And this is, of course, an idealization, but approximately conforms with the real world QCD, or the part of the QCD which features 3 light flavors. And the essential feature is, of course, asymptotic freedom, which makes the theory weakly coupled at short distances and ultraviolet complete. And then it has the global symmetry U3 cross U3 to begin with, but the axial U1 is anomalous, does not survive quantization, and the global symmetry of the quantum theory is then SU3 cross U1. And the vacuum does not, or the vacuum spectrum does not reflect this symmetry directly, but it reflects it indirectly in the sense that there is the vacuum condensate, the chiral condensate, which then leaves only the subgroup of SU3 cross U1 visible in the spectrum. In addition to 8 massless Goldstone bosons, which then in the case of light quarks are light so pseudo Goldstone bosons. And this is the sort of story that we know well, and quantitatively this has been confirmed in the lattice simulations of the theory. So here shown the results from 2 different lattice calculations dating back some 10 years, when it was then finally achieved that the control from the light scales to the heavier scales, and inputting 3 mass values then yields the rest of the meson and baryon spectrum as a prediction. So that's quite a good statement on one hand for our understanding of the QCD dynamics, and on the other hand for the development of these non-perturbative methods which are required to carry out these analyses. All right, so then moving again a little bit closer to the actual question that we want to address here, is that in QCD, all these bits of our knowledge fall nicely in place, but what happens if we would change the parameters? Consider other gauge groups, so other numbers of colors, and the other global symmetry, other number of flavors. And we will restrict a little bit, so we will focus on the SUN gauge groups and some number of massless Dirac fermions in a single representation of the gauge group. So denoting that by R. And as a function of these parameters, we want to determine the vacuum phase of the theory. So to get started, let's seek guidance from perturbation theory. So I'll be looking at two-loop beta function, and the small NF story is well known. That's the QCD-like part. So the beta function totally negative and asymptotically free, but then chiral symmetry breaking confining in the infrared. So that's for small NF, and then for large NF. So large enough, where enough is defined by the one loop coefficient of the beta function. So given here, and in terms of the group theory factors, so C2, the quadratic Casimir, and T, the normalization of the generators, NF, the number of flavors, and R denoting the fermion representation, and G denoting the adjoint representation. And as is well known, the beta function of non-abelian gauge theory encodes the interplay between the screening of the matter fields and the anti-screening of the charged gauge fields. And for example, putting in the numbers, fundamental representation, we find that the beta function, or the one loop coefficient of the beta function, changes sign around NF equals 16. And asymptotic freedom is lost above that. So we want to be below this number. Above, the coupling runs as in QED, so the beta function is totally positive, and as in QED, there's no anti-screening, there's only screening, but in the non-abelian case, for large enough NF, the screening of the matter just overpowers the anti-screening of the gauge fields. So the interesting region then is the intermediate NF. So now here also, just for concreteness, showing the two-loop coefficient of the beta function, again in terms of these group theory factors and the fermion representation and the gauge representation, the adjoint representation.
Sorry, Kimmo, I have a question.
Oh, absolutely.
It's in just the previous slide, yeah, trying to understand the physics of it. So this number is just something that comes out of the equation. We don't have a physical reason for it. For the number of flavors. Yeah. Yeah, it just comes out from the equation. But of course, I mean, it has the physics is that there is the screening of the matter and the anti-screening behavior of the gauge fields, and then the amount of matter is controlled on one hand by the number of flavors, but then on the other hand also by the size of the representation. So if you put it in the higher representation, then the TR will be larger, and then, as we will see shortly, less flavors will lead to a loss of asymptotic freedom if you put them in the higher representation. I see. Yeah. Thank you.
All right. So back to this. So now we would like to look at the so we are below the boundary where the asymptotic freedom is lost. So beta naught is positive, but then we can look at the sign of beta 1. And it turns out that the beta 1 changes sign at the lower value of NF than the NF for the loss of asymptotic freedom. And so there's this intermediate range. So NF AS, this is the boundary where asymptotic freedom is lost. The one loop coefficient of the beta function changes sign, and the NF star is the value where the second coefficient of the beta function changes sign. And then we are interested for the values of NF between these two extreme values. The formulas are just given here for concreteness, that this is something that you can grind out from the perturbation theory formulas. And now that the beta 0 and beta 1 are of different sign, then there can be a fixed point. And this is given by the ratio of the two coefficients. And this means that the renormalization group flow is non-trivial. So at short distances, you have the Gaussian fixed point, which controls the UV behavior, asymptotic freedom. And then towards the infrared, you don't confine, but you flow to a non-trivial infrared fixed point. And then the question is that is that really there? Because of course we are now working with perturbation theory formulas, and they might imply that this value of the coupling at the fixed point is actually large. So whether there's the question arises that whether there are some strong coupling phenomena that might affect this behavior. Of course, in the limit that you are very close to the upper boundary, so very close to the value NFAS, but a little bit below it, then the fixed point coupling could be perturbative. This is the so-called Banks-Axe region, but for the let's say integer values of NF, which conform to physical realizations of these theories, the value of the fixed point could be large. The coupling at the fixed point could be large. So still working with this within an analytic approximation, we can try to put in some information about the strong coupling behavior. So whether there will be chiral symmetry breaking or not. And one way to estimate that is to take the gap equation for the fermion propagator and truncate that in some approximation. So take only a subset of diagrams appearing in the iteration of the gap equation. And one such approximation is the so-called rainbow approximation. It's uncontrollable, of course, but it gives you a sort of clue about the physics going on. So so the statement from that is that couplings larger than some critical value will lead to chiral symmetry breaking. In other words, to the existence of a non-trivial solution to the gap equation for the fermion propagator. And the value is pi over 3 C2, depending on the fermion representation. And now the issue which is relevant for us is to compare this with the fixed point coupling obtained from the two-loop beta function. And if this critical coupling is larger, then the strong coupling phenomena are beyond the fixed point, and we might conjecture that the critical point, as implied by the two-loop analysis, exists. And carrying this out then leads to another boundary value for the number of flavors. So taking the alpha star or the G star from the previous page, comparing it with the alpha C given here, gives a constraint which can be solved for a critical value of NF, above which the fixed point exists and below which the strong coupling, the chiral symmetry breaking, sets in. And again, this is the formula in terms of the group theory invariance. And then, so then comes the question about the dependence on the fermion representations. So then you start putting the fermions in different representations and see what happens. And with Francesco Sannino, we showed that there's quite a few representations which are relevant. So for higher representations, you just lose asymptotic freedom so quickly that there's really no room for the conformal window.
So how much is known about the tree-loop beta function? I
mean, you could, of course, do that. Well, there's the one good feature with the two-loop beta function is that it's scheme independent. So the two first coefficients of the beta function are scheme independent. So in that sense, for a sketchy analysis like this one, it's sort of better. We know, I mean, the beta function is currently known for these theories up to 5-loop order, but that all then all the coefficients beyond the first two are scheme dependent.
Yes.
So, and anyway, so to build on this answer to your question, so we can now plot the sketches. So I'm saying that these are the sort of sketches for the phase diagram to guide the thinking. And for that, the two-loop, restricting to the two-loop is a sort of natural thing to do. So here, I'll show the...
Well, I'm slightly concerned with the sign of the thing. You've got a negative sign there, but if I take a Padé summation of it, the sign has disappeared. I get something completely positive. If I say, well, it's actually the first coefficient divided by 1 plus the they say, and expanded back out, that's an equally good approximation to this order. So
that's yeah. So, I agree. So and I don't. yeah, I'm saying that okay. So let me fix some approximation.
No, that's okay. But I was just wondering if there was some information from Tree Loop that would help me in that regard.
Yeah. I see. But and likely yes, and there are in fact proposals, for example, for the all orders beta function and related stuff. But the sort of for the point that I'm about to make, you resort to some approximation and see what comes out, and then take that as a motivation to try to do actually a real first principle calculation. But I see your point, and I totally agree.
Sure. All right, thank you.
So now sketching then the phase diagrams resulting from this approximation. So here so this is NF, NC, and R dependence, and the upper line on each of these colored bands is the boundary where you lose asymptotic freedom. So that's the where the first coefficient of the two-loop beta function changes sign. And then the purple one, so this rising band corresponds to the fundamental representation. And this cyan band corresponds to the two-index anti-symmetric representation. And the dotted lines, the cyan dotted line is barely visible. The dotted lines correspond to the boundary where the second coefficient changes sign. And the boundary of the shaded band corresponds to this NF critical, where the strong coupling phenomena approximated by this result from the gap equation for the critical coupling sets in. And yeah, so for NF equals for NC equals 3, the two-index anti-symmetric coincides with the fundamental, as we know that the two-index anti-symmetric is the anti-fundamental of SU3. And then another picture, which then contains the two remaining interesting representations, the two-index symmetric shown with magenta and the adjoint shown with green. So for adjoint, nothing depends on NC. That's because all the group theory factors are equal to NC, and they just cancel from the two sides of the equations. So this is now the intermediate result, or the motivation, that in these representations there is a chance that the conformal window exists. So does it exist? And so to summarize these motivations, so do we understand the dynamics at strong coupling? And if we did the first principle study, then we could perhaps draw these phase diagrams, the sketches of the phase diagram in ink, instead of just sketching them with a pencil. And then there is, of course, phenomenological motivation. So how we ended up on this actually historically was that the light Higgs could emerge. So if there was a strong dynamics underlying the Higgs sector, a light scalar dilaton could emerge from a theory close to the conformal window, but still confining in the infrared. And then more phenomenology motivation is provided by the possible composite dark sectors, how the composite dynamics would affect the form factors, which would be visible in the direct detection experiments for dark matter particles, for example. But all this is then kind of dependent on the baseline model. And now we would like to understand first, in more general, the big picture of what kind of theories are close to the conformal window, or which theories are inside the conformal window, and then which are QCD-like. So I'm not so much now leaning on particular phenomenology motivations, but more on the motivation of understanding these behaviors in general.
So question?
Yep.
By composite dark sectors, you don't mean a dark sector that is kind of extended. You actually mean that it's made or it contains composite particles.
Yeah. So basically, like some dark QCD, just existing on its own in its own sector.
Yeah. And it could be a multi-component.
Could be a multi-component and could have some non-trivial connection with the standard model. But again, that is something which is very delicate model building per se.
Yeah.
And sort of rests then on what we understand about strong dynamics.
Yeah, thank you.
So just to keep on summarizing the motivations. So since in any ways the lower boundary of the conformal window is at strong coupling, we need to apply first principle methods. And in the case of non-supersymmetric theories, this means lattice. And then I think it is well over a decade ago, the initial investigations in this led to establishment of a new field inside the lattice field theory, and it's known as lattice BSM, and it's currently a sort of grown and matured, and there are about 50 to 100 people working on these questions. And I will be describing, when I show the results, I will be describing the results from the Helsinki group. But then when summarizing, I'll also discuss then in a wider scope the results from different collaborations. All right, so just very briefly about lattice simulations. So the basic idea is to compute observables by discretizing spacetime and generating field configurations to evaluate directly the path integral. And the discretization means that the spacetime is taken as a hypercubic grid with some lattice spacing, which you want to take to zero in the end to get into the continuum. And the lattice sizes currently possible are of a few tens in each space-time direction. So it's clear that this is a computational grand challenge and requires a lot of computational resources, and that's then why one has to find good collaborators in a lattice group who can do the job and who have access to good computational resources. And then in the gauge theory, the gauge fields are represented by SUN matrices, the so-called link variables on the connecting the two space-time points with each other. And then for fermions, there are many realizations, and they have different problems and different benefits. We will be considering or using the Wilson fermions, and there's a lot of methodology, a lot of intuition, which has been developed over the past, I guess it's closer to 40 plus years of lattice simulations, mostly aimed to understand the vacuum of QCD. And so this is a relatively busy slide, just 2 or 3 main things that on the lattice, you set the boundary conditions for the fields, and then you need the action. And for the gauge, the action is the so-called plaquette action. So the little box corresponds to a trace of these link matrices around a square on the lattice, and then you need to sum over all directions and over all lattice points, and that's the Wilson action for the gauge fields, and this then in the continuum limit reduces to the continuum action plus the relative lattice artifacts which appear at order a squared. So that's the precision here. But then the Wilson fermions. So the action written here is, it looks deceivingly like a Dirac action, but it is really a lattice derivative which has inside it lattice artifacts which are of order A, and so it's a relatively less precise than the gauge action. And for the precision, then one has developed different methods called improvement, which means that one adds higher dimensional operators to the action to cancel these linear lattice artifacts. And this is called the Clover improvement. And it's controlled by this coefficient CSW, which is set to, on the tree level, it's equal to 1, and that is what we will be using. And then there are various techniques which improve also the gauge part of the action by smearing the gauge field in a particular way. And the bottom line is just that one has a action on the lattice with all the bells and whistles, and then one goes ahead and sees what that implies. And now
so just the improvements that are used here, are they simply to remove the lattice dependence of the action as written, so that if I expand it, I get leading terms to a higher order, or are they semantic?
To order a squared, and then the improvements are also implemented. So this smearing is implemented mainly to allow for simulations at stronger Baire coupling.
So what the latter comment is, that semantic improvements you're referring to?
Yes. That too. I mean, this hex smearing is a slightly different thing, but one could also do semantic improvement. But yeah, for the reasons that I think are explained on the next pages,
okay,
that's not as beneficial, because it rests a little bit more on the weak coupling, on the weak coupling properties of the theory.
Oh yes. So the primary thing is just to get something with an action which, when expanded out, has in corrections to what order do you aim for? It's only a square.
Right. So the Clover is to cancel the linear artifact from the Wilson fermion action.
What is Clover?
It's a higher order derivative expansion of the Wilson.
Basically, yes. I mean, I think that the origin of the term is that when written in terms of the link variables, it sort of draws a clover leaf on the lattice.
Exactly. The alternative way of explaining it is to say that, well, any higher order improvement is going to go to next nearest order and next nearest order interactions, and you build an appropriate set of lattice connections that cancel what you're trying to cancel. And it has that clover shape as the end result.
Yes.
Okay.
All right. So given that, so like I said, there's a lot of development which has been going into that over the decades, and it's mainly to address the analysis of QCD. And then the sort of naive idea would be that, well, I mean, you have your improved action, and then I just want to look at the different theory than QCD. So let's just grind through the machinery as usual and see what comes out. And this, of course, is too naive. And the reason is that for QCD, much of the development and much of the analysis was guided by the fact that we knew what the vacuum of the QCD looks like. But now, when we want to look at more general picture or more general theories, we don't know. That's what we want to find out. So we want to find out what the vacuum looks like, and we want to sort of know it or learn it by without ending up on the lattice, just analyzing lattice artifact. So let me try to make it a little bit more concrete. So in QCD, the essential property is that the asymptotic freedom sets in precociously. So on a lattice, which is accessible in simulations, you have the strong coupling phenomena in the bulk, and then you have the weak coupling on the boundary. So you can connect between the strong and weak inside sort of single simulation. I mean, it's not exactly that simple, but you can sort of achieve the change from the strong to the weak in a very manageable setting.
Do we really know QCD vacuum? For example, the theta sectors. That is also difficult to simulate in lattice in Euclidean formulation.
Yes. Yeah. Okay. So let's say that in order to determine the spectrum and determine the chiral symmetry breaking or the confinement, this is what you can do.
So you did not answer. So one does not, and the possibility of a theta sector still is being ignored in this calculation.
The topology, you mean?
I mean, it affects the spectrum, it affects the structure of the vacuum, many things, no? CP violation is introduced.
No, no, it doesn't. I don't think it affects here.
I don't know. I'm asking.
That one can, yeah. I mean, so one can work in the sector, in the topological sector, which doesn't run into these problems.
But the problem I don't understand is in the Euclidean formulation, the FF dual term has an I in front. So even simulation becomes a problem.
Yeah, unless it has a huge effect, you can use reweighting to take it into account, and you can. That's reasonably consistent if it doesn't have a very significant effect on the vacuum.
Yes, but one does not know that.
No, but one can check for consistency. I mean, if it's a large effect, then you're going to run into problems. Absolutely.
This I don't understand, because all the theta sectors are super selected. There is no even scattering won't link them. So one would not know by looking at theta equal to 0 what happens at theta equal to pi, for example.
Theta equals pi can be difficult to get to. I would agree. Yeah.
Or theta equal to something. They are super selected, so they are not related by any observable. This is just a question.
But it's just a term in the action which you can include. You can include it by as an you can treat it as an observable and take ratios.
No, don't go. Okay. I don't understand. Okay, but anyway, we can.
Yeah. Okay. So let's move on. So what I wanted to say here was that that you can connect from strong to weak coupling, but when you have a theory which which might have a fixed point, then the coupling is large everywhere. So it runs very, very slowly. And on the accessible lattice sizes, you don't really see such a strong running as in QCD-like theory. And so the figure here actually shows on the right, shows a sort of strategy that one might want to, or that one might apply. So there is a zero of the beta function, and the coupling is different on the each side of the zero. If you think about the continuum beta function, then whether you are on the asymptotically free side of it or on the other side of it. And then this is something that one might hope to see in the simulation. So the sort of forward and backward running of the coupling. So we aim to measure the coupling, and then one needs some definition for it. And there are different possibilities on the market. And one which has been quite popular and has been applied a lot recently is the definition using the gradient flow method. And the gradient flow means that you take your 4D gauge field and then use that as an initial condition for a flow governed by the pure gauge action in a fictitious fifth dimension. And this diffuses the gauge field on the lattice, so it smoothens it out in particular size, and renormalizes basically the observables. So it diminishes the ultraviolet noise and makes the measurements more precise. And then take an observable, the energy here, which can be evaluated also in perturbation theory, and use that as a definition of the non-perturbative coupling. And then this defines the flow time, basically defines the scale of the coupling, and the scale is related to the size of the lattice. So it's a fraction of the lattice size, and this then basically defines a scheme in which this coupling is defined, but nevertheless gives the opportunity to observe how the coupling changes as a function of the scale. So this is the operative definition of the running coupling.
And presumably you have G, the first one, T is a typo there in your expectation value.
Sorry?
The first T is presumably a typo. It's G mu nu of 0 on T, presumably. Or in the definition of E of T,
yep,
you're using two different times, presumably. Or am I not understanding?
No, I mean, this is just defined at the, I mean, this is just G squared at T.
So it's a composite operator.
Yes.
Okay.
Yes. And then right. So after the definition, so let me just move on to the results. So this shows an actual result of a measurement in SU2 gauge theory with 6 and 8 flavors. And so the different colors, different symbols correspond to different values of the Baire coupling. And then the x-axis shows the different lattice sizes that were used. And as you see, there is some non-monotonous behavior on each curve. at the smallest lattices. So those are just dropped from the analysis, and only the lattices above the size 10 are considered. And then already here, one sort of sees this forward, backward running. So the infrared is towards the right, and there seems to be sort of two trends. So already from this, one might think that there might be a fixed point around g squared of 6 for the 8 flavor theory, and g squared about 12 or so for the 6 flavor theory. But of course, this must be made much more precise. So this is just the raw data, and then one wants to quantify the running. And that is done using the step scaling, which is basically just dependence of the coupling when you double or triple or scale the size of the lattice, given some initial value. So let me try to walk through these pictures. So you start with some lattice shown on the left here and measure the coupling there. So this gives you the value u, and then you scale by, let's say, factor of 2, and then you measure the coupling again. And this gives you then the function sigma, which is called the lattice step scaling. So the value of the coupling when the lattice size is scaled by a factor of 2 and given some initial value of the coupling. And then you would want to do this again, so double the size again. But then the problem is that now the coupling on this lattice at the second grid from the left is different than the initial one. So then you do a scaling, a matching, that you change the bare coupling or the lattice spacing, so that this lattice with the new size corresponds to the value of the coupling which you originally had, and then you multiply by or scale by a factor of 2 again and measure the coupling, and then you get the value of the step scaling when your lattice size has changed by fourfold, given the same value of the initial coupling. And then you go ahead, you scale your lattice, and then you match the coupling to correspond to the one which you initially had. And then you have constructed this function sigma for that particular value of the coupling. And then you change that particular value of the coupling and redo. And now this is the place again where the difficulty of the slowly running coupling versus QCD-like running shows up, that this scaling and matching becomes very delicate. You would need a huge amount of data if you were to do this with the data alone. And that's why in these theories, it's better to parameter or to fit the dependence of the measured coupling on the bare coupling to facilitate this intermediate matching steps when performing this scaling. All right, and then this is just written down what I just explained in words. So again, a bit of a busy slide. So the definition of the step scaling, this is what was explained in pictures on the previous page. So the value of the coupling given the particular value before the scaling. So the step scaling tells how the system reacts on the scaling of the lattice size. And then one wants to go to the continuum by taking the limit of a goes to 0. And to facilitate this step scaling, one does an interpolation to the data of the measured coupling versus the bare coupling, and then do the limit by extracting this leading lattice artifact, which is expected to be A squared. And then the A independent part then gives the continuum step scaling. And this step scaling function is because this is now the behavior of the coupling. So it's like an integrated beta function. And then for the slowly running coupling, they are sort of proportional. So this is an approximate relation, which is quite well satisfied in the theory where the coupling runs slowly. But of course, one doesn't need to. I mean, in the continuum theory, one is interested in the beta function, or one starts with the beta function. But for the interpretation of the results, we can just as well look at the step scaling. So what the zero of the beta function means is that the coupling doesn't change, and then that means that the fixed point is signaled by the fact that the step scaling versus the coupling is equal to 1. So that's what it means, that the coupling doesn't run if you are at the fixed point. All right, so let's see what this then looks like. So this is again using the raw data. So the lattice step scaling for different pairs of systems. For NF equals 8, that's a factor of 2, and for NF equals 6, that is a factor of 1.5. And C, this was the factor which was related to the choice of the scale as a fraction of the lattice size, so 1/3 and 0.4 in the 8 flavor case. And it seems to be that there is a zero or a fixed point where the step scaling versus the coupling reaches the value 1. And then there are perturbation theory curves which seem to be compatible with the data. Of course, these are in MS bar scheme, which is a different scheme from that, and so it doesn't really, there's no meaning in a head-to-head comparison. And then this is then turning the results, so taking the continuum limit and turning the results into turning the step scaling into a beta function. So the blue shaded region here is the continuum extrapolation of the beta function, and telling the same story as the largest lattice sizes here, that there seems to be a zero, a non-trivial infrared fixed point at about GF. So the coupling equals about 3 for NF equals 8, and a bit larger for the NF equals 6. And then for these theories, we also looked at the slope of the beta function at the fixed point. This is the leading anomalous, the leading irrelevant anomalous dimension. So scheme independent, and the values of those were also determined. And then in an earlier work, we looked at 2, 4 flavors and the NF equals 10, that's we also looked at that on the lattice. The results are basically compatible with the 0 of the beta function. So this is very close to the practically this is a Banks-X region, in a Banks-X region. All right, so then let me just dig a little bit. So these were more recent than this one, but this is interesting because this was the first case that we looked into already in 2009, and this is the SU2 gauge with 2 adjoint fermions, and that was sort of much development in the methodology has been done since, and we have also since then redone the calculation in the Helsinki group, and several other lattice collaborations have also studied this theory, and the results are compatible with the fact that there is a fixed point in this theory. And just marketing this as a sort of first observation of a infrared fixed point in this type of theories. So I'm closing on my summary and conclusions. So the motivation was to see if we could actually draw the phase diagrams with ink, and the picture which is emerging from the lattice calculations is that for NC equals 2 and the fundamental representations. So these figures show the gray shaded band is the semi-analytic approximative sketch expectation for the phase diagram or for the conformal window, and then the squares here are computations from on the lattice with different numbers of fermions. So for 6 and 8 and 10, it seems that there is a fixed point into a color theory with fundamental fermions, and 2 and 4 are outside the conformal window. And then for SU3, there are values of NF 16 and 13, which seem to have a fixed point. And then there are numbers of flavors for which the existing results are slightly controversial. So whether 12 and 10 flavor theories are in conformal window or not. And for the fundamental representation, these are the values of NC that have been studied on the lattice. For the adjoint, this is the 2 flavor theory, which I showed on the previous page inside the conformal window, and also the theory with 1 fermion, 1 flavor seems to have a fixed point. This is done by another collaboration. And then the 2 index symmetric representation for the F equals 2, this just coincides with, for NC equals 2, this just coincides with the adjoint. So the same result as on the plot in the middle. And then for NC equals 3, seems to be outside the conformal window. For NC equals 4, seems to be outside the conformal window. So this is where the current state of the art concerning this particular question lies. And like I said, this is a compilation of results from several collaborations, which then, in addition to measuring the running of the coupling, have determined the corresponding anomalous dimensions and measured the spectra and other observables as well. And so here I just state the results from the literature for the anomalous dimension of the quark mass at the quark mass operator at the fixed point. So for SU2, and the results seem to be nicely compatible with the expectation that so inside the conformal window, near the lower boundary, the gamma star is larger, and then it decreases towards the upper boundary where it should become perturbative. And then for the fundamental representation, a similar story inside the conformal window. And then for the SU3, so depending on the collaboration, if they found a fixed point, then they were able to find the fixed point value for gamma. And then there is then the results that they quote. And then just the final remark, of course, refining this picture with maybe few more numbers of colors, and refining the behavior of SU3 for 10 or 12 flavors. And then it would be nice to check that whether the adjoint representation indeed is independent of the number of colors. And then further directions are the possible investigation of multiple fermion representations. So for the conformal window itself, but then also for the phenomenological applications, that how with many fermions in different representations, you could approach the conformal window, but still then deviate from that. So whether one could realize some kind of a walking technicolor theory or not remains as an interesting question. Multiple fermion representations are also interesting for phenomenological applications. And then a not exactly a to-do, but something which has been considered recently is the investigations of non-asymptotically free theories. So now we were focusing on whether there is a conformal window and whether we can discover that. But what about if we are above it? Can we say something about those theories? Can we study them on the lattice? And it turns out that one can. And for example, the Helsinki group has looked at the SU2 with 24 or even 48 fundamental flavors. This is just, of course, more towards the showing that in principle it can be done. But then there are interesting possibilities if one would add scalar fields and whether one could realize asymptotic safety. So the non-trivial ultraviolet fixed point. So I think I have arrived at the end of my slides, and I thank you. Thank you for your attention.
Thank you very much. The floor is open to questions.
Yeah.
Can I ask a question?
Go ahead.
Okay. First, I like the talk. I mean, it's the first time I'm hearing about Francesco, but after a long time. How is he? General question. Is he okay?
Francesco, oh, I think he's doing fine.
Okay. The question I want to ask is, when you say conformal window, I suppose what we mean is the beta function vanishes. Okay?
Mm-hmm.
The question I want to ask is, does it mean or imply that Beresford algebra emerges, or does it mean anything like that? Or is there a Cast-Moody algebra there? Is there a central charge there? Or it is simply a word for beta function management?
Yes, because this is I mean, of course, this is a theory which is conformal in the infrared. So
that doesn't matter. Beta function. So
it doesn't identically vanish, but it only vanishes at large distances.
At the fixed point.
Yes.
At the fixed point, beta function is 0, I suppose. No?
Yes.
At that point, is there a conformal group, a proper conformal group there? If there is, the vacuum changes because it depends on the central charge.
Well, it's 4 dimensions, Val, so it's
that doesn't matter.
It would depend on, I think the question would be, is it an A type, or there are four-dimensional analogs of central charge, which classify that?
The Beresford algebra is universal. It happens also in 4 dimensions. Okay? Because it is just algebra.
The Beresford is the algebra of the diffeomorphism group on the circle. It's related to it. So why would it be universal? There is a conformal algebra in 4 dimensions.
The conformal algebra has a central charge because the representation theory of the conformal algebra, the conformal algebra is not presented in dimensions. It is presented like that, no? In math groups, it is some particular type of algebra which has modular automorph, modular category and so forth. No?
I think this is probably a question for Werner.
So I would ask a relation.
I have a question, Mr. Nixon. I mean, depending on how you do it with the OBE, or if you try to do it algebraic or whatever, there should be a conformal theory. And presumably that can be studied, for example, by bootstrap methods. And then one could check the conformal dimensions. Has anything been done in this direction?
You can.
The question. The question is, if you're sitting at the fixed point, as one would expect, there should be a conformal field theory.
Yes.
And the conformal field theory will have a set of conformal dimensions, which in principle could be computed. There are various techniques for doing that. Bootstrap type techniques come to mind. Have any of these been used and helped to identify the dimensions you expect here? I believe that's the question, Werner. Is that correct?
Let me ask. There was a. Okay, I mean.
Let him answer first, Bal, before, just so we get some progress.
Okay, my question is not that. If there is such a thing, we know that in the conformal algebra, the vacuum structure changes. The representation structure changes with the central charge. Where is it reflected in the QCD in these calculations? Because there was a statement originally by the speaker that the theta vacuum doesn't matter. Because you also confirmed it.
Well, let's postpone that, because he is asked. There are 3 questions. Then let's answer the first one first, because it will clarify the answer to your question, Val.
Okay.
The one with regard to the conformal field theory.
Yeah, there have been development, I think, towards this direction, applying the bootstrap, and but I have not been myself involved in that, and I don't really know the details. So
let me ask a related question, okay, which at least for me looks like a very important development. It has been last few weeks. I think I talked here in the DIA seminar. The axiomatic quantum field theory people, namely Mund, Schroer, and I think Raren, they have put out a papers, and before that also papers, giving a very explicit demonstration that already in QED, there are uncountably many supersession sectors. Okay? And one checks from, so it completely changes the structure of the vacuum. The vacuum is, there is no pure state in QED, provided you take into account the infrared divergences. That depends on the scale. Okay? It is a scale dependent statement, so presumably at finite energies, it doesn't, some above an energy scale, it doesn't matter, but the scale is determined by the infrared dressing. Definitely that same thing happens in QCD. I have no idea whether it affects all these calculations. In other words, the QCD vacuum, slightly more rigorous sense, is infinitely degenerate. There are uncountably many superselection sectors. They may not affect the calculations in perturbation theory, but they exist. So they have some physics. So this is a general comment, okay, which, by the way, in these models, you cannot write a Lagrangian. In these proofs, they cannot be reproduced by Lagranges. So there is this whole thing that is developing by the side, and they don't seem to be addressed in these investigations.
No, he is very clearly working with a Lagrangian now.
Huh?
He is very clearly working with a very well-specified Lagrangian.
Yeah, but there is no, I don't understand. You cannot write a Lagrangian for those models.
No, but in this talk, he's dealing with a Lagrangian. So
yeah, also. So the physics side, they said affect the. So our concern is not how the calculation is done, how it reflects in physics, observations. That is not clear to me. Just a general comment. Another comment is you get this vertex operators intertwining this different irreducible representations, different superselection sectors. It happens that they obey a conformal algebra. That they have not been investigated, but there is a conformal algebra with a central charge. But they have not been investigated. So conformal algebra seems to be the thing that is under one way of influencing the different superselection sectors in QED and QCD in all gauge theories. So because of the massless particles which are there. So at least for me, it is not clear what, how these things intertwine.
are there other questions? Just Venus, I think you had a question. Just get back to the talk.
My questions are very, very simple.
Simple questions are always welcome. They
Okay.
clarify it for everyone.
Yeah, oh, well, this one, wait for this one. So I was just going to ask, like, I'm impressed with the progress that the Helsinki group has done. Just wanted to know, going from SU2 24 fundamental fermions to 48, how much computation power do you need?
Well, that actually was not such a big change. So actually, it was a little bit surprising how easy it was to do the simulations for a very large number of flavors. And I think that the reason there is pretty much the same as it is for QCD in the case of this precocious asymptotic freedom. So there the running is also very, very fast. Mm-hmm. And one starting at even if one starts at very strong Baire coupling, the system very, very quickly runs towards the what is called towards the free theory, basically. So it was not that the big cost in that case, actually.
I would expect there was almost no cost because you integrate the fermions out and treat them as pseudo fermions, and yes, you just sprinkle them as Gaussian. So there's almost no cost.
Yes. Yes.
And then, if I may, another question that I had, you mentioned that composite dark matter models would be a motivation here. So has any work been done on that side? Do you know of, I'm guessing Francesco must have done some composite dark matter.
Yes, I mean, there has been, so you mean phenomenology or theory work or
yeah.
So yes, there has been various proposals for different scenarios, and then there also has been actually a lattice calculations of the relevant form factors in particular models. So I think the Yale, the US group has been pursuing this over the past years quite a bit.
I see. I guess SU2.
But of course, I mean, calculating cross sections and form factors on the lattice is then art of its own.
Yeah.
which we have not been involved in.
Yeah, I guess SU2 composite dark matter has been done, I guess, quite a lot.
Yes, yes. I mean, there is a simple, I mean, there even, I guess the most of the focus is on QCD-like theories, but just focusing on the fact that if they are composite, then they will affect the precision observables and the phenomenology of the scattering.
I see. So that's how you would be able to tell the difference between a composite dark matter or fundamental.
Yes, I think the main motivation there is that maybe you could hide them better than because you see in the most vanilla models, the problem is that in order to produce Rayleigh abundance in the early universe, you need to have large enough cross section, and then that coupling feeds into the direct detection cross section, and that you would want to make as small as possible in order not to be seen, or to avoid the present constraints, which haven't found anything.
That's right. Yeah. And one last question. I kind of got lost in the mathematics of the whole thing, and I didn't get the final point. But so, what do we know about the vacuum phases?
So so if I go to my real summary slide, so that's what we know, or what we think that we have achieved is that the gray bounds, these are the cartoons that I started with, and so sort of proposals that that whether to what extent do we see this, and then on the lattice, so small numbers of colors have been looked at. So NC equals 2 for these 3 different representations, and the results seem to indicate that the 2-index symmetric one, that's seems to be the lattice results seem to be fairly compatible with the expectation from these estimates. The 2 colors and 2 flavors case is sort of in this cartoon. It's on the very sill of the conformal window, but then for the adjoint, it seems that the conformal window extends somewhat lower than expected on the basis of this approximative estimate, and then same in the fundamental, at least for the SU2, and then depending on what happens in SU3 for 10 and 12 flavors remains to be seen, that how far down do these values extend. So it's like tinkering little pieces on top of the figure beneath, and that just reflects also the fact that carrying out the simulations is a major task, and the progress is slow, but what this sort of, in my opinion, shows that there is progress. And there are at least examples now of theories which do seem to feature the fixed point, the infrared fixed point, and that's actually now coming back to the discussion about the refinement or the further theory developments, that there might be an important interplay between the numerical or computational results and the analytical results that I think there's a good grounds for that there are now things which we do seem to gain from the non-perturbative computations, and then if that can be then used as a guide or verified in analytical settings, then I think there's demand for further work.
Yeah. So the reason I'm asking this is because I'm kind of trying to figure out how much information you can get on the symmetry breaking and maybe even the strength of the symmetry breaking in the dark sector to see.
Well, yeah, I mean, it depends a little bit on the question that what you want to answer in phenomenology. But I mean, if you think about, for example, the let's say the near conformal, the possibility of a near conformal Higgs, then the kind of natural model building setup would be to take a theory which is inside the conformal window but close to the boundary, because then when you couple it with electroweak, that will break basically the chiral symmetry, and that would push the theory out of the conformal window. So if you were looking for a walking theory, then it's likely to be a deformation of the theory which is inside the conformal window, but only barely. So in that sense, when you put something inside the standard model or couple with the standard model, then of course the sort of baseline changes a little bit. And there will be contributions which affect the long distance behavior and perturb it. But I mean that was sort of the part of the motivation that if you want to build phenomenology around some SUN gauge theory with some number of fermions, and then depending on whether you want to be close to the conformal window or you don't care, then if you want to be close to the conformal window, then these studies can provide information which might be valuable in the phenomenology or model building.
Can I try a couple of slightly more technical questions just so I can get a little bit more from it? Your final slide there has some conformal dimensions. Can you give an idea of the error on those? I'm looking at the NF equals 6 and the NF equals 2 in the adjoint. 2 adjoint has 6 fermions and NF equals 6 has 6 fermions. So I'm wondering, are the 0.2 there within errors of one another? Can one?
This one you mean?
Yes, and the one above it.
Yes.
So they both correspond to 6 fermions. So.
Yeah. Okay. So
I'm just looking for some universality here as well. Just.
Yes.
You've quoted 3 decimal points in one. Can I believe those 3 decimal points, or is it really 0.2 plus or minus?
Yes, I mean there is a plus or minus. I don't quite remember now the numbers. They can of course be checked from the references. I think this one has a relatively large error on it.
Okay.
Yeah, I see. So yeah, in light of what you are thinking, I think I think it might be that these are compatible. Well, this is relatively large. Yeah, I mean we should check from the references. I mean they certainly have
the second question is the glue ball mass in these cases, has it been measured, or what do you know about it?
Yes,
is it...
that's also a very good question, because that is there have been calculations of the spectrum, for example in the SU2 and adjoint with adjoint fermions of the the meson and the also the glue ball spectrum, and then I'm not exactly sure if that has also been done for the fundamentals.
Well, I'm really wondering what is becoming massless here. What is taking part in the conformal thing? Assuming there is a conformal
Yes,
theory
yes.
here.
Yeah, I mean, of course, yeah. So if you think about the meson masses and how they scale towards zero as the function of the quark mass, yeah, that's one way to infer the gamma star.
Okay, so the mesons are becoming massless.
So basically, I mean, of course, if the theory is conformal in the infrared and the relevant perturbation or the relevant operator is the quark mass operator, then as you scale the quark mass towards zero, then all the masses should scale to zero in proportion to that, and that's, I think, what the simulations also see. So
and you think, and does that include the glue ball mass?
In some cases, yes, but the glue ball measurement is, of course, very noisy. So okay. It's not as easy to extract as the let's say a pseudoscalar or the vector. Mm-hmm. Right. But to that, let me also add that there are also other methods to obtain the gamma star, and in many cases it has been obtained from the step scaling of the pseudoscalar wave function renormalization. So
is there any theoretical result to compare with? And is there any theoretical computation to compare with? Because I can get it from the fixed point. If there is, assuming that there's a fixed point here, I should be able to extract it as anomalous dimensions from the fixed point.
Yes. I think that for these numbers, they are all based on either the extracted from the spectrum or from a lattice calculation of the pseudoscalar wave function renormalization, or from the eigenvalues of the Dirac operator. Okay. So that's the and in some cases there has been also shown the consistency of the different methods, so that they imply the same compatible values for gamma star.
Okay, so there's no field theoretic computation to compare with.
No. Except, of course, in the Banks-X region, where this is in fact the value of the perturbation theory calculation.
Yes. But just back to your point, Bal, the vacuum changes at the conformal point. Of course, there's a mass gap has developed. So the vacuum is dramatically different at that point, but one can still access it in simulations like this.
Yeah. One can or one cannot. What is?
One can.
Okay, then I would like to know what it is.
Well, I mean, the vacuum structure of a gapped theory is very different from the vacuum structure of an ungapped theory.
Yes, that's all. That is what I am trying to understand, where they appear in these calculations.
Well, they are coming out from that, measuring the glue-ball spectrum and from measuring those critical exponents, for instance. The fact that you have a region where it looks, where you can see some scaling, that is telling you you've got a very different structure to exponential fall-off. Yes,
I agree with that. But if you are, I mean, glue-ball spectrum, by the way, has been calculated by Mohull. And Sachin and so on.
Well, not for this theory. I mean, they could do it for this theory.
I agree. But are we trying to make any statement about nature or just internally?
Internally at the moment. Because there's no reason to believe that this is the theory of nature. But if you find something that looks tempting, maybe it does prove to be nature.
then
I
there
think
is no
that's his. I think that's Kimmo's hope, is that it may turn up to have some relevance to dark matter, where we have no idea what's going on.
That's just the opportunity, right?
Yes, I understand. Yes.
I'm not taking a big stance on this. But yeah, but I mean, of course, I mean, in the spectrum, in the measurements of the spectrum, as a function of the quark mass, the pseudoscalar, of course, shows the different behavior with in these theories, where it just scales to zero linearly with the quark mass, and then if there is chiral symmetry breaking, then it scales as the square root.
But your theories have all zero quark mass.
Oh, yes. But of course, I mean, one can study the approach as a function of the non-zero quark mass.
Yes. Yeah.
And that's, of course, what one does when one wants to look at how the spectrum scales.
Okay.
Towards.
Right.
Why did you say that you develop a mass gap at the beta function 0 point? Benjo was mentioning.
I was. The mass gap goes to zero, is what you expect, Val.
Yes, it will become a continuous spectrum, I think. No,
That's what one expects. Yes.
Then the theory completely changes.
For the degrees of freedom that are participating in the conformal theory.
Yes.
Other things will decouple and
That's
become
what I would
irrelevant.
expect. Yeah. So that is an important point, because the theory completely, the structure of the theory changes.
Exactly, that's what I'm saying. Yeah.
Okay. The second question is, I remember that when the theta vacuum first appeared in the literature, there were a number of papers to compute the vacuum energy, okay, analytical calculations. And I remember, I think Ed Witten had a paper and some others had papers. And for small theta, the claim was it goes like theta squared, like cosine theta, something like that. No?
Yes.
That is my recollection. Okay? But at theta, then as theta increases, and the spectrum changes, the masses change, everything changes. Okay?
Absolutely. No, I completely agree. Yeah.
And at theta equal to pi, then one doesn't know what is happening. Yeah. So it is not clear to me that these calculations are not affected by theta vacua.
Oh, presumably they would be if he included them, but he is assuming that it's zero because that's the simplest thing to do.
Okay.
And he comparing with lattice computations, you can reliably do it for that, but you can reliably get small theta by reweighting, but only small theta.
But there is a problem, because these are lattice calculations in Euclidean domain.
Yes.
Then the topological term appears with an I in the Euclidean domain, and then you know that simulations become highly dubious.
Yeah, no, that's why I'm saying you'd use reweighting.
Okay.
Which the errors become large as the effect grows. So it's a difficult thing, but you can do it. It's just pretending that this is an observable in the system and calculating ratios of averages. But the ratios of averages are going to have large errors if there's anything significant happening.
Okay. That is why you talked about ratios.
Yeah, that's it's called reweighting in the lattice community.
Okay, fine. Okay. Anyway, that talk was very educative. Okay. Many things to learn.
Yes, yeah, thank you very much, Kimmo. Yeah. Perhaps I will, if there are other questions, let's...
I do have a question.
Yeah, okay.
But I want to allow other people to ask questions if they have any.
No, Venus can continue, I think.
Good, okay, yeah, so this question is just because you mentioned in your motivation baryogenesis, I just wanted to ask if these sort of setups would have any implication for baryogenesis.
Yeah, okay, so I didn't take that as a particular motivation, more than just a general statement that there needs to be something beyond the standard model, and that's why looking at the strong dynamics might be generally useful. But of course, again, I mean, if you have new composite dynamics hidden or elsewhere, that also affects the phase transitions in the early universe.
Yeah, I was thinking, since you can kind of embed the Higgs mechanism or whatever, the electroweak symmetry breaking in here. Yeah, of course, I mean, the problem with baryogenesis in the standard model is that we don't have enough CP violation. Yeah, but at none of these kind of symmetry breaking scales can you have a spontaneous CP violation. That's basically what I want to ask. If you break your whatever SUN to its subgroups until you get to the electroweak phase transition, can you produce some CP violation from the spontaneous breaking of the theory?
I don't know immediately. Yeah, I don't know immediately
Yeah.
how that could go.
Yeah. Yeah, as Paul said, it's very educating, and
maybe we can thank Kimmo again and just stop the recording. Okay.
Right.
Okay.
Yeah.
Right,
Okay.
Yeah.
Okay.
Thank you so much, Kimmo. I really